and I'm going to share. Congratulations. Like I said, we finished define. And I mean, the level of intensity goes up a little bit as we keep going. It kind of peaks at the analyze phase, and then it goes down. So kind of we're working up today, nothing too heavy, a little bit of homework as you'll see. But here we go. So just quick review. DMAIC, history, roles, responsibilities, what the belts mean, defining our project, making sure we do a real good job. You know, again, most of our time is going to be spent in define, measure, analyze, you know, when we're any kind of project, really. Because if we do those well, then the project is going to go good. The improvements will be good. Everything will stick, the whole 9 yards. And we got the project management basics. That was probably the low point of the whole class because it's all about just listening to me for a little while. And then we got into some FMEA last week, really fun tool. And then the Toyota production system and lean finished last week. So today we move on to 3 weeks will be in measure. Trying to cut it to 2, but I think it's just easier. Like today will be like 35 minutes, 40 minutes maybe. Not too bad.
Okay.
Not too many slides. And then the M's in about understanding the current process and how it's measured and its historical baseline performance. You know, so that's the key thing is, you know, so many times when you're doing improvement work and you ask the person, hey, how often does that happen? All the time, or every 2 weeks, or, you know, this is really about gathering data. Like Six Sigma is about data. And that's usually the biggest challenge is, all right, we got a problem. How in God's name we're going to measure it? That could be the hardest question you have to answer. But once you do that, then we can move on to the analyze, improve, and control. So we're going to cover today's a little kind of fun. We're going to cover process definition. So we, you know, in the define phase, we have a problem statement. And then we wanted to start to define the process better in the measure phase. And it starts with some tools like process mapping. We're going to cover that, particularly swim lane map, a tool called SciPoc. And then I'm going to get into some value stream mapping and some basics on how that works. You guys may know some of that. And then a tool called XY matrix. And then we're going to just begin the Six Sigma statistics this week, basic statistics and data collection. And then next week, we'll get into descriptive statistics, distribution normality, central limit theorem, graphical analysis. Sounds complicated, isn't it? It's so easy. It's so easy. And then we get into, then we'll get into gauge R&R, you know, looking at our measurement system, making sure that it's repeatable and reproducible, and get into some process capability to finish out the measure phase. I think someone had requested me to send out the PowerPoints ahead of time, so I did that today. If you check your email, you'll see the measure slides that are there already. So without further ado, process definition. So what is a process map? Let me, I'm going to grab my presenter view. So what's a process map? It's a graphical representation of a process flow. And again, guys, I think the big takeaway from this course, I hope, is that very few of the tools that that we're going to talk about, you do alone. You know, and I think, you know, for those of you guys that are doing A3 or whatever form of continuous improvement you're doing, you know, it's always better in a group. And these tools you can't really do by yourself very easily because they're really about making sure that we gain agreement on the current condition in the measure phase. And that, you know, the measure phase is about getting the current condition right and making sure that before we solve a problem, we understand the problem we're trying to solve. And the process map, it visualizes the business process step by step. So you could pick any process you want. But just get together. How do information or materials flow from one business entity to the next? And it depicts the input and output of each step. And the project team should map the current state, not what we want to see, but what is it right now? I know I got Matthew Schwartz on here. We're doing a lot of this at Atlas right now. in terms of understanding the current condition on a bunch of business processes. And the purpose is to identify the complexity and also maybe some redundancy. You find out who's doing the same thing, who's entering the same information, who's typing in the same things over and over. But you can identify and communicate the focus of the problem solving. They're living documents. They're not meant to be etched in stone. You date them 11/13/23, and that's what we got today. And they may change. Especially if you do a lot of continuous improvement, they change pretty rapidly. And the benefits are we can identify important characteristics. What are all our process inputs? What are our supplier requirements? What are our outputs? What do our customers actually need? What are our value-added and non-value-added process steps? And we're going to cover more of that when we get into value stream mapping. Again, remember that value-added is the steps that your customer will pay for. And again, your customer is whoever you hand your work to, or also the person that might pay the bills. So you might have, you have two customers usually. But value-added means they'll pay. Non-value-added means they're one of the 8 ways. Defects, overproduction, waiting, non-essential processing, unnecessary transport, inventory motion, and unused employee brainpower. Data collection points, it identifies those. When do we, cycle times, defects, inventory levels, cost of poor quality, etc. Decision points are identified and who has to make those decisions. And that's usually a big a place for waiting. The waste of waiting is usually decision points. I got to give it to somebody to prove it, or someone has to sign off on it, and then process control needs. So here's how we do it. This is a regular process map. one of these monsters like that. So first we identify the beginning and the end. And this is very similar for swim lane map, which we're going to get into in a minute. And we need to have the process owners, right? The people actually do it, to understand how the process is actually performed. And this is where that concept that we talked about define called the hidden factory, or just because that's what the work instruction says, doesn't necessarily mean how the process is performed. So this is why it's so important that people that actually do the work, and being able to put a map together and we could all agree to, yeah, this is how it's done. We record the process steps and then sort them in the order of occurrence. And we fill the step information, plot the diagram. And once completed, record and document the map. So if the process is too complicated, then you can do, if it's, for one map, you can do additional sub-process maps. But here we have a start and a finish. The diamonds are all decision boxes. And the work just flows from person to person. I like the swim lane maps. Dan, you might have been involved when I did it at Ulrich Steel. We did a whole workshop on it. Picking a process. And then the only difference is like a swim lane where this is department A or person A, department B or person B, department C or person C. And this is really, really good because as lean thinkers, when we do a swim lane map, every time I cross one of those boundaries and I have to hand my work to somebody else, it's usually hours, weeks, days, months. There's time that's waiting usually because it has to go into another queue. So just by looking at the number of times a process goes from A to B to B to A to A to B to C to B to A, there's a ton of opportunity for improvement there. And the SIPOC, I'm gonna ask you to do a little bit of homework on this. But basically it's kind of a cool little diagram, very similar to a map, where what we're interested in is suppliers, input, process, output, and customers. And it's, again, a high-level visualization tool to identify and link different components in a process. It's usually applied in the measure phase so we can better understand the current state. It's something, again, like all these other tools, that doesn't really work all that great alone. But the homework's going to be by alone, though. So we're going to do the best we can. And so the SIPOC stands for suppliers. Those are the people that provide raw materials, services, and information to the process. Input is the raw materials, information, equipment, services, people environment involved in the process. The process itself, the high-level sequence of actions and decisions that transform our inputs into outputs. And the output is the services or products delivered to the customer, and the end users or recipients are our customers. And the benefits of a SIPOC is it gives more detailed information than process maps, demonstrates how each component gets involved. It helps visualize a narrow scope. It serves as a great communication tool to help different process owners understand the entire process, not just their little piece of it. And it's often helpful to include suppliers and customers that are exterior to our building. And you always start with the process. So I'm going to show you some examples of some SIPOCs that the last class did. And I'll probably ask you guys to pick a process. Could be feeding your dog, giving the baby a bath, whatever. You'll see some pretty cool ones, how to paint the house. But it starts with the process. Get that, all the steps, one through whatever. And then you move on to outputs. What are the outputs for those processes? And then you go to customers who benefits from the process outputs. Then we work back to inputs. And then we work back to suppliers. Here's a cool example. This is my friend Sean Hassett from Ulrich Steel, like 3 or 4 years ago when he took this class. Feed the dog, open the cupboard, get a bowl, fill the bowl, call the dog. And then it's interesting because he actually amended this to I have to get medication for the dog too. I got to get, go to pill. So that would be an input and a supplier. I have to go to the vet, to get the pill or whatever. And the outputs are dog eats, dog fertilizes garden, and the customers are the dog, the family, and the garden. And you work back. I have to go shopping, buy dog food, return home, put groceries away in the cupboard. And my suppliers at a grocery store, in the case of medicine, the vet. So that's SIPOC. Now I'll show you some more examples to give you a few more ideas for the homework. And value stream mapping. This one's a little more complicated, but this is a really cool tool. But it's a method to visualize and analyze the path of how information and raw materials are transformed into products or services that customers receive. PTA's done a lot of work here. Value stream mapping. It's useful to identify, measure, and decrease the non-value added steps in the current process. The difference between a value stream map, as we're going to talk about now, and a process map is that the value stream map, you're actually counting time. So you're just measuring time and reflecting it on the map. Where on a process map, as you saw before, the swim lane, there's no time, there's no measuring there. All right, so this is probably a primary lean tool. There's a book called Learning to See that came out, I don't know, 25 years ago. That's kind of the Bible for value stream mapping. And typically there's all kinds of software you can use to do value stream mapping. The good old-fashioned way is a clipboard, a piece of paper, a pencil, and some kind of a timing device. And again, the non-value added activities, as you map the process, and I'll show you what that looks like. Those are the things that do not add value to the products or the service customers or service customer demand. They're just waste. And those are the things that by visualizing, using a value stream map, and A3 teams, groups really makes this process easy and fun. Not all non-value adding activities are unnecessary. There's things like safety, I mean, you can't charge extra for safety, right? You have to do it. There's a lot of regulatory stuff, aerospace has a lot of ISO, things like that. Those are part of the process. They're not value adding, but they're necessary. In other words, your customer won't pay for them, but we have to do them anyway. So we want to make those as lean as we can. And value stream map, so you plot the whole high-level process from when the order gets placed and how much they want to when the customer receives it. So all the processes from when an order gets taken to the time it gets shipped. And it requires more detail than the regular process map, like the swim lane map I showed you. Like we need to know things like cycle time, prep time, setup time, available time, how many hours a day we work, how many hours a shift, excluding breaks. We need to know our scrap rates, rework weight. So there's some homework that goes into building this map. And we assess the value stream map of the current process, and it helps us identify and eliminate opportunities for waste. There's one. This is the classic that comes right out of Learning to See. The way the map works, it starts in the top right corner at State Street Assembly there. And that's customer demand. State Street Assembly is the customer. We're making up customer name, obviously. And that's where you'll see how many shifts we have. They all go in that dialog box right below. How many shifts we have and how many minutes, hours that we have per day. All right. So like if it was an 8-hour day, hour for lunch makes 7 hours, 2 15-minute breaks. We're down to 6.5 hours a day of actual work time. And everything moving from State Street Ascent from the top right to the left is about how our information gets translated out onto the floor to get things made. It's, in a ziggity-zaggity line like this, it means it's all electronic. You're not handing a note to somebody or anything like that. And a lot of times there's forecasting, there's production control, things like that. As we move to the left corner of the map, we find our suppliers, so in this case, Michigan Steel Company. And generally, you look at, our major suppliers. We don't look at every single thing, if we buy from every supplier when we do a map. And then so basically it starts at 1 o'clock here, State Street, goes counterclockwise to production control. Our information flows to the left. Then you can see the arrows going down. That's giving information from production control to each of these cells. The assembly 1, assembly 2. There's welding, assembly 1, assembly 2. You can see them down here. And then, so our suppliers get notified. And then anything you see a triangle, that's inventory. And you'll see that from Michigan Steel Company, it gets to us by truck. And there's there's a number of coils that are already in stock. And in the triangle, it says 5 days. That, again, that's how things are measured in value stream mapping is time units. And then you can see a ziggity line down the bottom here where we're going to start to add up our process time, our production lead time, which is how long it actually takes from the time we get an order till the time we ship it. And then underneath it, you can see as the line goes down, this ziggity line, how long does it take to actually do the work, right? And the cool thing is, if you add up so inventory is counted as 5 days, and then in between stamping and welding, number 1, there's an inventory right here too. So and that's 7.6 days worth of inventory. So inventory counts as time in lean thinking. And then you'll see like a dialog box under stamping, for example, where you can see what's our cycle time, what's our uptime for the machine, how much time is available, how many operators. Usually the number of people working is either smiley faces, that are drawn on the map. There's an entire, almost like the old maps that we used to, Rand McNally, when we used to have to travel, we didn't have GPS. I don't think maybe nobody on this call remembers that. We used to have a book, and there was codes for the roads and for everything on the map. But point 2, the big point here is, and then the other thing I want to mention is you can see the arrow between stamping and welding number 1. It's a jagged, thick line there. That means that whether welding 1 is ready or not, whatever we stamp, we're gonna push to them. So it's not a pull system. And the big number, again, the most important part on the map is that where the circle is there, because usually, we say, hey, if a customer says, how long does it take? 2 weeks. The amount of actual value-added time where you're actually transforming the order into something you can ship is usually more like 185 seconds, and everything else is waste. So that's where you might say, oh, look how much inventory we got. 7 days of inventory in the stamping. Maybe we should set up Kanban, or some kind of a pull system there. and then we can reduce that 7.6 days down to we want 1 day's worth or something like that. But that's basically how the value stream map works. The best way to learn it is to get involved on a team that's doing one. Again, people in Oxford, PTA, we did one with the Cat One assembly, and we're able to, transform, from hours to minutes. I think it cut 2.5 days off the order. Spaghetti chart. Any questions? I'm sorry about value stream mapping. Again, the best way to learn it is when you have an opportunity to try it, on a team. Anybody? Any questions? I know I went fast. Everybody cool?
Yeah,
Everybody breathing?
I think so.
I don't hear any snoring.
I'm good.
All right, cool.
I'm good.
The next tool, a lot simpler, spaghetti chart. And it's a graphical tool to map physical flow of materials, information, and people involved in a process. It can reflect distances between multiple workstations. And again, it's, motion and, is one of the ways, along with weighting. There's a whole bunch of problems with having things spread way apart, right? And this is how we might optimize motion of materials, information, and people. And the reason they call it spaghetti diagram, because a lot of times it looks like a dish of spaghetti when it's done. This one on the right is actually Matthew Schwartz, I know, was on here, and Sebastian from Atlas. This is one particular part family of a washer they sell to Pratt & Whitney. And you can see that the course starts in the material crib, and then it goes to these particular functions, and you end up at the end of it at 270 feet of walking. And there's opportunity there to consolidate things, move them closer together, things like that. And so you create a map of the work area layout, observe the current workflow, and then draw the actual work path. Guys, for those of you who want to do lean for a living, there's nothing like a pedometer. Putting a pedometer on people, in terms of how much they're just walking, to get their job done on a daily basis. And we don't really pay attention to it until people start having sore backs and sore feet, stuff like that. But I think you'd be amazed at just how much unconscious walking we do in the course of a week, and again, it's a great tool when we're doing spaghetti charts, because you can put the distances real easily. And we want to just cut out all that walking, because the customer's not paying for it. And I guess you can make an argument that it's kind of a good health program. Everybody hit their motion moving goals for the day on their iWatches. XY, I'm going to go through real quick too. This is another tool that's used in the measure phase, but it's a tool to help us quantify subjectively. This is definitely a tool we want to use with a group. The relationship of several X's to several Y's. And among the Y's under consideration, two important ones should be the primary and secondary metrics. So it's about, all right, we defined our problem, in the define phase. And now it's kind of digging a little bit deeper here, and looking at the primary and secondary metrics and identifying those and quantifying them. It's kind of like, it reminds me of PFEMA a little bit, FMEA. Remember last week where we're going 1 to 10 for likelihood of occurrence, impact if it happens, and how easy it is to detect. Kind of similar, where we're kind of arbitrarily picking some ratings and then quantifying, multiply them together to find out, let's focus on the X's with the greatest influence. And this is what it looks like. It's just a table, really, where the customer requirements, the Y's, are on top, and then all my input variables. And again, remember in Six Sigma, as we move forward, a common theme is going to be, we're going to identify the vital few factors, and that Y is a function of X. Y is a function of a bunch of X's, where the X's are the input. And it's only 3 to 5 X's, or, very seldom 5 even. There's a few key things that we have to look at, that if we can control those really, really, really well, then we're going to be able to get the Y that we want. And then we're going to rank them, and, do the sum product of each cell value, and then the percent ranking, depending on which one has the highest percentage ranking, gaining agreement with a group that's doing this exercise. Those are the ones you attack first. So real simple example would be, this is kind of what it looks like. Input variable x1, x2, x3, all the way to x7. And then output y characteristic y1 to make a little bit more sense. And as you can see, as you're rating them 1 to 10, you just multiply them all together. Whichever one has the highest, you're going to go after first, which would be input variable x5 would be something we'd probably attack in x4 and maybe x1, or I'm sorry, x2. There's a real example of it. So let's say voice of the customer, IT help desk. We could all relate to that. The voice of the customer is I need fast and easy to get help. And I might get these things through a survey. I think, what's the most important to you when you call the help desk? Well, I want to make sure that I get fast and easy to get help. I want more knowledgeable agents. I want minimal PC downtime. I want to be able to improve my PC performance. I want better communication on changes. So here's the priority is high priority is 5, 4, 3, 2, 1. And that's from a customer survey, asking your customer, voice of the customer stuff, right? And there's a bunch of ideas, that might be able to impact these. One might be add more phone agents, more desk side assistants, improve self-service portal where people can learn to fix their own stuff, better agent training. Maybe there's some self-healing programming that can be done. Maybe we publish a newsletter. So each of those X's has a ranking also. And the idea is that, you multiply them all together, add them all together. In this case, 10, 15, whatever, 97, you get the ranking. And you could see that self-healing for known problems would be one thing that we'd attack and try to control the process. Maybe add phone agents and better agent training. Anyway, that's the idea of the XY diagram. Nothing on the exam on this. It's just something for your information that you might find useful in the measure phase at some point. All right, enough fun. Now let's get into a little bit of Six Sigma statistics, and basic statistics. We're going to cover this the rest of today, and then as we get into next week. This is this one slide here. It's going to be with us till the end of the class, right? From now till the end of the control phase, because we have to know what kind of data we're looking at, right? Continuous data is data that we can measure, right? How long, what volume, how far. Discrete data, it also includes, sometimes it's called attribute data. It's counted. So continuous means measure. Discrete means counted. How many, how often, yes, no, pass, fail, things like that. Those are the two types. And the reason why it's important, it sounds simple, is because depending on what kind of data, as we get into a whole bunch of Six Sigma tools and statistical tools, which one you use depends on what kind of data that you have. All right. So just remember, because I'll be probably asking like church from now on, and I'm hoping that you guys will perk up and tell me the answer each week. Continuous means measure. Discrete means count. That's all. And then, of course, these statisticians try to complicate things. And there's 4 different types of measurement scales. And I wouldn't get too bogged down with these 2 slides. I'm just going to kind of cover them for you. The most useless one is nominal. The most useful one is ratio. So it goes from simplest, nominal, to the one we're all used to, which is ratio. And just give you a quick description. When we have data, we want to apply numbers to something. And nominal means we're just labeling them, right? I have 11 yellow, red, 18 red, 3 orange, 5 green marbles. And it's just names, labels only. No ordering scheme is possible. The central location is mode, and mode means it's the central location is the one that happens most often. So in this case, red would be the mode, right? As for information only, useless. Please don't think another thought about it. Now, ordinal ranking, is a little bit more, and that's it's used to label variables that have a natural order but no quantifiable difference between the values, like satisfaction level. Very satisfied, satisfied, unsatisfied, satisfied, very satisfied, extremely satisfied, something like that. Um, Product defect by type, and the central location there is the median, which is the central, the one that's in the middle of all the data that's collected and measured, and the dispersion. How do we measure dispersion? Is with percentages. So 50% of the people said that they're very satisfied. So that's what we get out of ordinal or ranking measurement scales. And then we move on to interval. It's a scale to label variables that have a natural order and a quantifiable difference between values, but no true zero, like temperature. Temperature is a good example, like in Celsius, right? There's no real true value, zero value, because you can go below zero. Um, SAT scores, things like that. And then ratio is data that normally we collect where um, they have a natural order, quantifiable difference, and a true zero. Height, weight, length, um, temperature, all that kind of stuff. All right, that's enough of that. I think it's just confusing to me. Um, Population and parameter. So the definition of population is all possible observations of similar items from which a sample is drawn. So in statistics, and particularly in Six Sigma, we are never dealing with an entire population of data, right? We're not going to sample, we're not going to test every single piece that comes off our machine and measure it, right? We're not going to send everything to quality control. It's always going to be about a sample, right? But if we did do that, like let's say we want to know the weight of killer whales, I guess we can theoretically try to kidnap every killer whale in the world and weigh it. But obviously, if we want to understand the weight of killer whales, we're going to come up with some kind of a sampling strategy, that is a lot more economical. That's going to make sure that we're pretty close to our population. And you're going to see this as we go. That this is the strategy as we move forward in statistics and in Six Sigma. A parameter is the arithmetic description of that population, all right, of that population value. And it's often unknown. It's estimated by a statistic. And that would be a good example would be the weight of all killer whales, right? We don't know what the weight of a killer whale is, but we can estimate it using a statistic. And now this is what we'll use most of the time is a sample, which is a randomly selected set of units or values or items that are drawn from a population, right? And you see this in polling all the time, right? They don't go out and poll every single person. It's a randomly selected, it could 2,600 people, whatever, but it's supposed to be representative of the population. And a statistic is a numerical value taken from a sample data set used to make an inference about an entire population. Right. And some of the notation that we're going to use, you'll see this this slide for a while, over and over during the class. I wouldn't pay too much attention or try to memorize anything, but these symbols all represent something we're going to do with the data. And most of the data we're going to look at is going to be my weight that I take every Friday and my blood pressure back from 19, like, I don't know, I think there's 700 weeks worth of weight data, my own weight, that you're going to be able to use some of these things with. Guidelines for collecting data: define what's to be measured, what characteristics are to be measured, select the right measurement tool and techniques, establish who will collect the data, select an appropriate sampling method, decide who will analyze and report the results. All right. So in my case, my weight, my heart rate, and my blood pressure. And those are the characteristics. Using a scale and a cuff on a Friday morning, I do the collecting, I do the sampling, and you'll see the report. And two types of sampling techniques: random sampling. It requires giving every part an equal chance of being selected for the sample. and the sample must be representative of the lot. And stratified sampling would be sampling from a subgroup of data that reflects a population parameter. For example, what's the average height of children in third grade? So I'm not going to text every third grader on the planet, right? I'm going to get a sample there. And boom, we're going to pick it up next week with, we dive really deep into descriptive statistics. I want to switch over to math practice real quick so I can show you the homework and what our status is so far. So starting with the status, everybody see that okay? This is what I have. No worries. You know, if you read, you know, I'd like to have it, you know, as we go, because it's going to start to build. And then there's, you know, sometimes I'll have a help class, you know, as we get into this a little bit more if you need it. But I just want to, all I'm hoping is that you'll take the time to practice some of the things that we're going to be giving you. Particularly as we get into, you know, like descriptive statistics, normality, correlation, all that stuff. Everybody did a nice job on Pareto. So SciPoc, what you're going to get is this table, not filled out, but here's a couple of examples. This was from Dan at King Industries last, one of his customers, I think, testing solids, painting a room's walls, Michael Vesicchio, remove furniture. So you start with the process, make a list of them, determine paint type, color, go shopping, buy paint, return home, paint store, home improvement store, walls are painted, walls are hole free, and making iced coffee in the morning. That was AJ King, Ulrich Steel. And there's rolling mill operation. Robotic end of arm tooling application. This was Lexi out in Colorado. I think she got the MVP on this homework. This was really well done. Again, process steps first, then the inputs. And I love it. You know, if you can use an actual process that you're using, guys, there's extra credit involved. I think there was a couple people last time, because you have the choice of either SciPoc or if you want to do a swim lane map. And I thought this was pretty good. This was Desiree out in Colorado, the PTA. And this was about a dentist appointment. Come on time. The hygienist brings you back, takes your x-rays. Dentist takes over for a quick minute and then gets noted in your chart by the hygienist again. Do I need a second appointment? Real simple, but get the idea. So, you know, so whether you pick this one or this one, the high achievers in this class over the last 4 or 5 years, and I'm not saying you should do this, they did both. So that I'll send you the math practice just like you see it with, you know, except blank, and that'll be the homework. 4:11, so we went 40 minutes. Everybody awake?
Yep.
All right. Any questions?
No, just a comment. I did send in my homework from last week, and on your chart, it showed that it was not.
All right, I will find. I'm sure you did, Kim. It's probably
Okay.
operator error. You know what I mean?
Just don't let
Okay.
it happen again, Bill.
No, I have to do a better process of making sure I get him. I'll mark that good. Okay.
Okay, sweet.
Thanks, Kim. Thank you.
No,
Sorry
you're
about that.
welcome.
Sorry
No,
about
thank
that.
you. I just want to make sure
All
it
right.
got in there.
Yep. Appreciate that. Anybody else? Did I miss the homework? Once the football season ends, I'm a lot more organized. 'Cause I'm traveling Friday, Saturday. All right, guys. Have a great night.
Thank you, Bill.
Thank you, guys.
Thank you, Bill.
I'll send the recording. Okay.
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 Thank you.